Hello everybody and welcome to today's lesson on multiplicities and graph reading. Our objective for today is we will analyze polynomial functions to determine function characteristics and the behavior near zeros. So let's start by taking a look at how zeros can happen for a polynomial function. I'm going to draw an example and I want you to draw it exactly the way that I draw it. Okay, starting from up here, our curve is going to go across the x-axis, straight line, and it's going to turn around, and then it's going to kind of like wiggle through here, going to keep going up, then it's going to cross the y-axis, coming down again, and then it's going to bounce off the x-axis to go back up. So here we have three places where our curve has contact with the x-axis, but in three very different ways. Our first zero, where the curve goes straight through the x-axis, is a single root. Then we saw further to the right where our curve kind of wiggled through the x-axis, and when we see that, then that's an indication for an odd multiplicity, and that means it needs to be at least 3. At least 3. And further to the right even, we see our curve had contact but bounced off the x-axis, and this is an even multiplicity, and even means at least 2. So if we now knew where those zeros were, we could go ahead and write a function from that. So let's just assume that this first zero was at -4, the next one was at -2, and the last one here is at +3. We can use this information to write our function f of x is going to be equal to, and now we're going to write it in factored form. Remember, the factors always show the opposite sign of the zeros. The first one is a single root, so that's x plus 4, close parentheses. The second one has a multiplicity of at least 3, so x plus 2 needs to be cubed. And our last one, x minus 3, is an even multiplicity, and that means that that factor needs to be squared. And here goes our function in factored form, written from just observing the zeros of the curve. In this context, we can now discuss a new concept that has to do with this, and that's the concept of turning points. Turning points occur when the graph goes from increasing to decreasing or vice versa. And if a function f of x is of the degree of n, whatever that number n may be, then that function can have at most n minus 1 turning points. Turning points occur when the graph goes from increasing to decreasing or from decreasing to increasing. In other words, they occur wherever we have a max or a min. And those are also our turning points. So in the graph that we have drawn here, we have a turning point down here where the graph goes from decreasing to increasing. Then up here somewhere close, maybe even at the y-intercept where it goes from increasing to decreasing, and then again down here where it goes from decreasing to increasing. 3 turning points in this example. 2 of them are minima and 1 of them is a maximum. Okay, then let's use this new acquired knowledge and apply it to an example. Given the graph of g of x, answer the questions. Our first question is, state the roots and the multiplicities. So where are our roots? We have one root right here at -1, and we have another one over here at +2. So our roots are at -1, and looking at it where the curve bounces off the x-axis and goes back down, that means we have an even multiplicity. And the second one at +2, where the curve wiggles through the x-axis, not going straight through it, that is an odd multiplicity. What is the degree of this function? We have one even multiplicity and one odd multiplicity, the even one of at least 2, the odd of at least 3. That means it has to be a degree of at least 5, and it will definitely be an odd degree. Okay, what are our turning points? I see 2 turning points here, going from increasing to decreasing at our first 0, and then going again from decreasing back to increasing down here. First one is a maximum, second one is a minimum. We have 2 turning points. And we can also talk about the end behavior. As x goes to -infinity, f of x goes to -infinity, and as x goes to +infinity, f of x goes to +infinity. We have one end of the graph going down and one end of the graph going up, which is what we would expect of any function with an odd degree. And since f of x always goes in the same direction as x, that also indicates to us that the leading coefficient of this function has to be positive. Now let's see if we can use this to actually sketch a graph without even using the calculator. F of x is equal to 0.01 times x minus 2 times x plus 3 squared times x minus 5 cubed. Let's first take a minute and describe what is actually happening at each 0. We have 2 as one of the zeros, and since that term has the exponent of 1, we have the line going straight through. Then we have -3 as another 0, and since this binomial is squared, we expect the curve to bounce off the x-axis. And then the last one at +5, we expect the curve to wiggle through the x-axis. Adding up all our exponents, 1 plus 2 plus 3, we get 6, and therefore the degree of this function has to be 6. So we're talking about a function with an even degree and with a positive lead coefficient up here. So we can describe the end behavior without even seeing it as x goes to -infinity, f of x goes to +infinity, as x goes to +infinity, f of x again goes to +infinity. Remember, an even degree and a positive lead coefficient means that f of x is positive both times. So now let's go ahead and sketch our function. We have one zero at -3. We have another one at +2, and the last one at +5. And we know that the curve goes up both times. So let me just draw some arrows here. And now let's see what happens. At -3, our function bounces off the x-axis. Bounce. And now we need to go up, and then obviously at some point come around, cross the y-axis, and go straight through at +2. Straight through the x-axis, that is. And we somehow need to turn around again. And now we're going to wiggle through at +5 and go back up to +infinity. That is what we would expect this curve to look like. Now, even though we did this without the help of a calculator at all, there's nothing wrong with using the calculator to check our work. So here I already punched the equation into the calculator. Let's look what the graph says. And looks very similar to what we have. There you go. That shows that our graph wasn't so bad, and we can obviously even use it to find the y-intercept if that is something that we needed to do. Okay, so much for this. Now go ahead and watch the second part of this tutorial.